Right, let's get started. So, starting today, we'll be doing some review of topic 1 to topic 2, topic 3, topic 4, and topic 5. I'm just be sitting here so everyone can hear me, and also the video can hear my voice as well. Disclaimer that in this session, we're not going to solve any questions together. We'll be just reviewing the concepts and just kind of revisiting our knowledge. Okay? So today we start with topic 1, the number and algebra. It feels quite a vast, various types of concepts included here. So I think we can divide this topic into 8 parts. Okay? The first one being the sequence and series. And the second part being the exponents and logarithm. And the third part being the proof, all types of proofs. I think we've seen that question today. And then also the binomial theorem. We also have permutation or combinatorics. And then the complex numbers. I think I forgot one. Of course, partial fractions. Lastly, the linear algebra. So we'll be going through all these sections loosely. I'll be just going through the formula, how to use them, some vocabulary, and some minor tips and tricks that I can think of. All right, so let's get started. Let's get started with the sequence and series, as they are the first ones to appear in our IB curriculum. So when we talk about the sequence and series, first of all, we have 2 types, right? Sequence, we have the arithmetic part, and then we also have the geometric part. Arithmetic is about the addition, and the geometric is about multiplication. And if you can summarize those 2 topics into one word, remember the common difference for the arithmetic and for the geometric is the common ratio. So that common difference in the common ratio, the d value and the r value itself kind of solves most problems for us. And also sometimes we forget the fact that it's the common part. The moment you see the word common there, it means that we can think of it as d1 is equal to d2 and r1 is equal to r2, which sets up an equation for us, which usually builds a stepping stone to solve a lot of problems. Right? When you encounter a problem and you don't know what to do, well, the easiest way is to somehow find an equation. Right? So finding the common difference, knowing that d1 is equal to d2 and such, is a good it's a good starting place. And also, maybe you should also talk about that sequence is when you have just the terms like the u1, comma u2, comma u3, comma dot dot dot, whereas a series, we have the u1 plus u2 plus u3 plus dot dot dot. So when you add the terms, it's series. Or we can also say that the series is kind of like the sum of the first 4 terms of the sequence. That is also another way to say the series. One more thing that I think that most people forget, especially in the geometric series, is about the infinite geometric series. By the way, some synonymous terms of infinite geometric series is the convergence, we say that the series converges is equivalent of saying that the infinite geometric series exists. And the third and the most important definition, which is written in the formal booklet, but people forget, is that the common ratio, or absolute value of the common ratio, is less than 1. And that's really important that you remember and that you include that somewhere in your solution of your problem. Quite often you'll be seeing some questions where it asks you to find the series or ask you to find a specific value, and you need to pass that test that the common ratio, the R value, is between -1 and 1. It is written so clearly in your formula that S infinity is U1 divided by 1 minus R, right? Absolute value of R is less than 1, but we just forget that in the middle of solving our problems. So just make sure that you have that under your brain, that during or at the end of your solution, you verify your results. Okay? Just like how, you don't have a square root of a negative number, or you don't have a division by a 0 or such. So make sure you have that in your head. One more thing to note is that the formula are available for the arithmetic sequence. Arithmetic series, we have 2 versions. So you want to choose which one to go for, whether you know the UN term or whether you know the common difference term. You can choose. The geometric sequence, the geometric series one, there's not much difference, so it doesn't matter which one you use. Yeah.
So for when we say convergent, divergent, we're talking about the sum, right?
Yeah.
Okay.
The sum converges or the sum diverges. Good question. I think that's about it for the sequence series. Do you have any questions about the parts?
So just this, sorry. So you would never say the series converges? You don't really say the sum converges?
Series is. Yeah. Okay.
The sequence is just like when the numbers are listed, not adding.
Exactly. Sequence is when you have commas. Series is when you add those numbers. This part, for me, personally, and for many other math teachers too, we all agree that sequence and series are straightforward because you have the formula, which means that you already have those equations already set up for you. So make sure that you use the formula and also those hidden formulas, such as finding the common difference, which is just one term minus the previous term, and the common ratio, one term divided by the previous term, and those formula, and you can probably set up a lot of equations, and one of them should be helpful for your solution of the question. Commonly, it's tied with the systems of equations as well, or also with the common ratio part. Sometimes you have those polynomial equations or powered equations as well. So look for those connections. Although quite often, every year, students seem to say that they suffer from sequence and series. In my opinion, after you understand it more, I think it's the most straightforward part. That's why it appears so early in the topic 1.2, 3, 4, and such. Anyways, let's move on to the second part, exponents and logarithms. Assuming that we all know and we're all familiar with the exponent laws, let's talk about the logarithm laws. We all have the logarithm laws in your formal booklet, ready for you to use. One thing, the 2 parts to note for is the existence of the log of a, base of a of x prime m, that we can take down that m. When you have an exponent in your logarithm, we can take it outside as a coefficient. Requires a special attention here. Another thing to note is the change of base law, we call. So the log of base of a of x is equal to log of base of b of x divided by log of base of a of x. Sorry. Oh, b of x, my bad. especially useful and this b value doesn't take any requirements, right? So if you want, you can swap it with some numbers that are related to x and a, so that you can easily represent the logarithms. So these two are useful. So although they're in the form of booklet, I just rewrote them. One more thing that we should be careful with. For me, it feels that a logarithm is kind of weird, and it's kind of, for me, it's quite difficult to follow the formula of just swapping the places of a to the power of x equals to b and is equal to x equals log base of a of b. So let's just try it at that. For example, we can try one, quick, easy one. X is equal to, let's say, log base of 3 of 27. Then this is one way to solve this kind of problem without the calculator. I don't know. I just wanted to practice that, just replacing the parts piece by piece. So that 3 is in the place of the base part, A. Let's write that. And then X goes on top here. And then B goes on the right hand side, 27. Especially when you try to go from the right hand side to the left hand side, I think people quite struggle. And then we can kind of deduce that, 3 to the power of something is 27, so we know that 3 to the power of x is 3 to the power of 3. So we conclude that x is equal to 3, and such. I just want to point that out because every time I do this one, I have to follow the step by step inside my brain. One more thing to note is quite often you see problems like this. A to the power of log base of a of, let's say, 5. Right? You're asked to evaluate this kind of problem. Let's say the question goes like this: evaluate. I mean, pretty sure after some practice you can get used to it and just say that the answer is 5. But if you struggle with that, like me, all the time, you can try to have that imaginary variable on the right hand side, and then you can try to solve it from here. So at this point, we can take the log of base of a. So then you can say log base of a of 5 is equal to log base of a of x. Then we can conclude that 5 is equal to x. So this is the method that I use. If I want to evaluate something like some weird shapes like these, then just introduce a random variable on the other side in order to solve that problem. Okay.
Doesn't a to the power of log a anything just cancel out to the thing itself?
Exactly, but I don't know. For me, it's not very intuitive. So I like to do the steps, especially when you have those. Let's say you have like a to the power of 2 of log base of a to the power of 3. I don't know. Sometimes you have those problems. Let's look at the cheat sheet. I think that's about it.
I think like it's also useful to note that like the reciprocal of the log, you can switch the like x and a.
Reciprocal of the log.
Like log a of x equals to 1 over log x of a.
Log base a of x is equal to 1 over log base x of a.
Yeah.
Interesting.
The way to prove it is using the one that we...
The change of base.
Yeah.
Yeah, it makes sense.
We were saying that it's 1 over, let's say, log base a of a divided by log base a of x, like this. Interesting.
Yes.
Cool. That's a interesting law. Nice. If you can have that in your brain, I'm pretty sure it's quite useful. Thank you for suggesting. All right. Anything else about the logarithms? We'll revisit the properties of logarithms and the behavior of logarithms when we talk about the exponential and the logarithmic function in tomorrow's review session. Otherwise, let's move on to the next part. And 3. What was it? 3. Proof. Right. So we haven't talked about proof for quite a while, so it's kind of over our head. Let's just mention some special types of proofs. The first one is deduction. Okay. What do we mean by proof by deduction? Proof by deduction, basically, we're trying to show that the left-hand side is equal to the right-hand side. That's our ultimate goal. And when we're doing that, just remember that there's a big wall between the left-hand side and the right-hand side. You're not going to do anything such as adding something to both sides, or multiplying something to both sides, or squaring something to both sides. You're trying to avoid that as much as possible. Instead, you're just evaluating and rearranging, simplifying and factoring those algebraic tools that we know, methods that we know, to show that ultimately the left-hand side is equal to the right-hand side. I mean, we can do some certain actions, but I think the best rule of thumb is to just not cross a boundary at all. Okay? That's the proof by deduction, and that's the basis of many other proofs. So we can use, like in the middle of proof by deduction, we can do other stuff, or in the middle of other proofs, we can use deduction. And it's the easiest one too. And that's why it's in the SL part. But if you try to go with the HL part, we have the useful one of induction, mathematical induction. Induction is divided into 3 steps. First one is to prove the first case. The first case of n is equal to k. This one, you can do the proof by deduction, or you can just do evaluation and such.
Would you put k as a number, right?
Yeah.
Yeah.
Sorry.
It would be
Let's
n
use
to
1
0,
for now.
Yeah. Usually.
Yeah, usually 1. Like for today's question, I think there was a case where the first case is n equals 2, then that happens. But yeah, first case, usually n equals 1, or n equals 0, or whatever that is. The second step is to write down, let's suppose that for n equals k, the proposition is true. And multiple times, when I look at the marking scheme, you're required to write this statement. Okay? It's not sufficient. If you leave out certain words from here, you lose points. You lose the reasoning points. So you have to say that suppose. Those are the keywords. Suppose.
Can you say assume?
Assume, yeah. Assume, suppose, similar. Or assume. Okay. Multiple times in the marking scheme, including the one that I've posted today, it tells you deliberately if you don't have these words, you lose a point.
When we were doing these questions, like when we actually learned it, we said P n equals K, and then we showed it, and then we just take this out. Would that be sufficient, or do we need to write it with words?
I think we should write it in words, just to be safe. Suppose that, or assume that for n equals k, the proposition is true. Okay? So make sure you have those vocabulary in there. And then lastly, you're proving. The proof for n equals k plus 1. The next step, right? Using n equals k. Because of the third step, it's important that we acknowledge clearly that we're supposing that n equals k is true, or assuming that n equals k is true, because we're going to use that case to prove for the next part. I think most times when you're doing induction, you kind of get lost because you're not using the n equals k case. Okay? Remember that when in the middle of proving the n equals k plus 1 case, it's important that we include that n equals k for sure. Okay? That should be part of your proof process. If not, the chances that you'll be having some difficult time. Okay? So make sure you include that. And when you're doing the part 3, definitely you can do the deduction, or you can do the other methods that we'll talk about. The others are etc. Worth mentioning are such as contradiction. One sentence summary of what is contradiction. Contradiction is proving that opposite is false. And so usually we see the case, prove that square root of 2 is irrational. Then we attempt to prove that the opposite is rational, and then we say that it's false. Okay. So contradiction is proving that opposite is false. Other type is the contrapositive. Contrapositive is if you're trying to prove that A implies B, it's equivalent of proving that not B implies not A. Okay? So if it's too difficult for you to prove that A is B, you can try to say that not B is not A, then that's sufficient as well. So those are contradiction and contrapositive. I think contradiction is used a bit more often, but contrapositive is also used sometimes. Also, there's the counterexample. Counterexample is usually a disproof. If you want to disprove something, we just find the counterexample of that. I think most cases we'll see the induction problems or the deduction problems. Sometimes we have the contradiction. They're part of the curriculum, so I cannot assure that's not going to be an exam. It may be, so it's worth mentioning. I don't think I've seen the contrapositive and counterexample too much, but they're also handy sometimes, right? For the ease of proof.
Wait, so for counterexample, you would just pick a number that should work and then when it doesn't, and you just like
Yeah.
plugging in a number.
Right. So the question should be, I think it should be deliberately telling you that disprove this proposition. Then you find a counterexample. But by the nature of it, I think it's just less exciting as a question maker and also solver for students.
Sort of trial and error.
Kind of, yeah. Trial and error to disprove something. So that's why it's not as commonly used in an exam setting. All right. Any other questions about the proof methods?
Wasn't there also proof by exhaustion, or do you think that did not pass?
Exhaustion too. Yeah, we can mention them, but it's not as commonly used.
I think it's just more time consuming, so I think.
Yeah, it's quite time consuming.
That's true. It's just the one thing that proof at least is not. You have to keep trying examples, right? Very possible. Or it's like oh, like this is not true for the k. It's not true for k plus 1. It's not true for
Oh,
k
so
plus
it's induction,
2.
but like.
Yeah, but you have to do it like a bunch of times. So like that's why I don't think
No,
they should do it.
like, for example, try to prove something by saying, okay, if all odd cases are true and if all even cases are true, then every case must be true. It's kind of like that, like having multiple categories for it.
Okay.
Yeah. I think we can
Segments.
leave the other ones
Like
for now.
multiple of 6, you do k plus 1, k plus 2, k plus 3, k plus 4, k plus 5, and then you finally install.
Yeah.
Something like that.
Yeah. I think we can skip the other ones for now.
Exhaustion is one.
Exhaustion and the contrapositive. Sure.
They're not important.
All right. Anyways, let's move on to the next part, the binomial theorem. A nightmare for a lot of people. So binomial theorem, let's look at the formula for them. So we have two versions of the binomial theorem formula, right? So we have the one case where we have the expansion of a plus b to the power of n. And the formula itself is pretty simple to use. Just note that the first version, the easy version, is useful when you have the n value, the exponent, as an integer. Okay. So you see that it's just going to be, for example, a plus b to the power of 5. Then you have the 5, and then 4, 1, 3, 2, 2, 3, and such. Whereas the second one is a bit more interesting and more difficult. is when you have the n value, the exponent, that is not an integer, one that is a rational number. For that, we need to be careful when we're using the extension. Quite often, it's more important that we know. The formula itself is just, you're just going to use them somehow. But we try to represent that binomial theorem as, for example, if you have, like, let's say, x, it says like 2 plus x to the power of 1 over 2, let's say. And what I suggest is you try to make it so that we're doing 1 plus 1 plus x over 2 or something like this, right? And then we have factored out the 2 to the power 1 over 2 in front of it. That's the basic idea of how the second version works. We try to leave out the first number a, that's just 1. So that's why you have that 2 to the power 1 over 2 here as the coefficient, a to the power of n. And then it starts by doing 1. Okay. So that's one thing that I wanted to note. Factor out 2. Another thing to note when we're doing the binomial theorem is we need to understand about quite often the question will be like, find the coefficient of, let's say x power of 3 term or something. And this happens especially when you're trying to find the binomial theorem of 2 different parts, and then you have to multiply them together. So when you have this case, IB exams are about time management too. So you need to find a quick and fast way to approach this value, right? To find the coefficient. So, devise a way to efficiently find the specific term, right? You don't want to start from term x power 1 term all the way to the x power 3, or especially if this question goes like coefficient of x power 6 term. For that, you can think of it like something x plus something x squared plus something x power cubed plus the dot multiplied by something x plus something x squared plus something x squared cubed. Then instead of going like, okay, I need to do this whole expansion, instead I can think of like, okay, if I want to find x power 3 term, it's gonna be the merging of the first part's x with the second part's x squared, or that merging. And then it must be the merge of x squared in the first term and the x on the second part, and such. So you need to be efficient on this. Okay. Because the expansion of polynomial times a polynomial takes a long time. I'm pretty sure we'll have some questions regarding the binomial theorem. So I think we can leave it on for now. Any questions about the binomial theorem?
Are these usually paper 2 or paper 1?
1.
I think it's mostly paper 1.
It's fun.
Oh, the thing about factoring out 2, is that just for the extension binomial theorem?
Yeah. Even for this one, even if you have the calculator, like there's nothing much you can do. So
On the text, they do a way where it's like x to the power of r minus something, and if you find r, you can do this or something like that.
yeah. We'll go through the questions on the exam, so it'll be fine. But yeah, my suggestion is don't be too scared by a binomial theorem. That's fine. They're nice. They're not too mean to you. Most times.
That seems weird.
The first one?
No, like,
The second part?
Yeah.
See, so if you're efficient, then it's less of a headache.
You're still doing it twice, that's me.
Yeah.
Once is more than enough.
Like today's review questions, we had one.
We did?
Like not binomial theorem, but it was kind of like this. To find the coefficient of the specific
The
term.
Maclaurin series.
Yeah, the Maclaurin series one. It's quite similar. Nothing much difference.
I didn't get that.
I did not do that efficiently.
We'll go through that question together. Right, combinatorics. 5.
Yeah, that's too good.
I know what it is.
Honestly, I could say it's one of my weak points.
It's all over.
So remember that we coined this mnemonic, is that what it's called? What is that called? Abbreviation? POC, no. Right? It stands for permutation, order. Combination, not order. That's our abbreviation. So permutation is order, and combination is not order. Permutation order means that, for example, if I'm taking the cards out of the deck, right, the order so that it's without replacement. Right? And then the combination, like without replacement. So the first place, second place kind of example. Whereas the combination is not order, so let's say like with replacement. Or like if you're saying choose 2 or something. Choose 2 out of 5. We have the formula for these in your formula booklet. The combinations and permutations. Also, it's worth mentioning that combination, by the definition, is always going to be smaller than the permutation. Right? Permutation has way more variety. Combination, because they're not order, and they're with replacement, so there's a bit less possibilities. The combination is always smaller than permutation. If you're confused.
Permutation order doesn't matter. No. Yeah.
Order matters, so there are more cases.
Oh,
Yeah.
that's yeah.
Because like A and B and B and A are different, so you have more cases. So that's why permutation is bigger. Combination is less. Other than that, other than using the formula or the calculator, I think I forgot. On the calculator, we do like math, right? Math, probability, and math, probability, NPR, NCR. We use the NPR, NCR on calculator.
And those are mostly on paper 1 or 2.
I think that it doesn't matter for this one because it may be mixed with probability questions as well.
What does replacement mean again?
Yeah. Okay. I'll explain the replacement part. So replacement means that when you're taking out a deck of cards, for example, and when you pick out one card, and then either you put it back in and then you do a remix and then you pick it out,
Oh yeah.
or you just keep pulling. Yeah. So like for example, if you're choosing like if you're choosing 2 cards out of a deck of cards, then it's without replacement because you're just going to pull 2 cards, right? Or if there's a chance that you get the spade of ace twice, then it's with replacement. So you put it back in and then you just shuffle again. In my opinion,
If it's like
Yeah.
you put it back, then you would like times it by the same thing. But if you don't put it back, it's like factorial, right?
exactly, yeah, that's the difference because you divide it by the r factorial. That's what makes the difference.
Is this like the sheep question that we did, like with the 6?
Kind
Oh,
of,
yeah.
kind of,
Yeah.
yeah.
That was
Yeah. So connection to that, we'll talk about that in class on Friday. But combinatorics is about the permutation and combination, but they don't have to be used all the time, in my opinion. Right? If you know the factorial part, we can use just factorial and our just way of thinking about numbers, and we don't have to use permutation and combination. Maybe I'm saying that because I'm kind of weak on the combinatorics, But I'm pretty sure, like for today's question, it was like something out of 4 points, and then the part B was out of 4 points as well, right? Don't skip them. But you have to remember that if you see that it's 4 points, it means that you're dedicated to use about 4 minutes for each question. You know, when I was doing the questions on my own, I definitely spent way more than 4 minutes. And that's because, it's not because I actually used 10 minutes to solve the part A. It's because that 6 minutes was for incorrect use of time. Right? So you want to try to find a way to get to the answer right away. And so that's why you have to try to think of it more systematically. How to find that cases, how to arrange the situation into systematically. I'll try to go over the methods of my thinking for that specific question later. But I think that's common. When I'm doing the questions, like the IELTS exam questions, I find it quite difficult with the combinatorics part. So hopefully you don't make the mistake. You try to find that specific use of time for efficient solution. We'll do this question on Friday, so we'll go over that. My point is that you don't have to use permutation and combination all the time. It's about counting principles, combinatorics.
I could never figure out what to do something.
Yeah.
It's weird.
I think it's about the practice too.
Yeah.
You have to practice well. Right. Anyways. Other than that, any questions about the counting principles? Okay, let's move on. Sixth part is the complex numbers. Let's do partial fractions first, and then we'll do complex numbers. I'm just gonna drink water.
Actually, the recording is still going, right?
Her voice was just included there.
Yeah. Hey guys.
Do you know that teachers, we learn from our B.Ed program, we deliberately do not use the term guys.
Big girl.
That's why I say y'all. Right.
Soft dudes.
He says that.
I've gotten a feedback when I did a sample lesson. I got a feedback from my advisor saying I use guys too much. I learned my lesson from there. Anyways, partial fractions. Basically, the idea of partial fractions. This one is quite tricky because nowhere in the formula booklet tells you anything about this. Basically, we're taking a rational expression of complicated part into addition of two rational expressions that are simple
B.
and simple, right? Not A again.
Why can't?
Sometimes.
Yeah.
Okay, basically, this is the idea. Right? We're trying to take a complicated fraction into addition of two easy fractions. Right? How do you do that? You do the equating the coefficients. I think it's pretty simple.
Top can have something too, right?
Sorry?
It doesn't need to be just one.
Yeah, it can be something else too. Let's call it C for complicated. Should we do one example here? I think it's worth trying. Let's do like 2 over, let's say, x squared plus 5x plus 4. Let's say.
Wait, can we do an example with partial fractions?
3 partial fractions?
Yeah,
Is it
that's in
okay?
the textbook.
That's in the textbook. Interesting.
Well, wouldn't that be just the denominator having 3 factors and just factor it out?
Yeah. So in that case,
Same thing.
okay, assuming if I have, I just can't think of a good cubic expression that is factorable easily. Do you want to make one?
Let's not.
Well, let's start factored. We don't really need to.
Oh, are you a genius? Let's start factor. Nice. That's a good idea.
Outside.
I like that. I like that. Okay, let's say we have such weird fraction, and we're trying to represent this as a over x plus 1 plus b over x minus 1 and plus c over x plus 2. Why are we doing this, by the way? Because when you're trying to calculus, or when you're trying to integrate or something, it's easier if you put them into different parts. So what do we do? We're just going to merge them together right away on the denominator side. But when we do that, we need to multiply our parts, right? It's going to be like a times x minus 1 times x plus 2 plus b with x plus 1 and x minus x plus 2 plus c times x minus 1 times x plus 1 times x minus 1. Basically, this is the idea of using the partial fractions. Afterwards, we're going to compute the numerator side, right? So it's going to be something here with 2 on the top here, and on the bottom we'll have the same thing. But we'll have some kind of iterations, and we're going to have something like, I'm going to use lowercase here, ax squared plus bx plus c, right? That's ultimate guideline, right? And then we do the equating the coefficients part. For example, in this case, because the left-hand side, the denominators are the same, so it doesn't matter. The left-hand side only has just 2, right? So we can say that a is going to be 0, and b is going to be 0, and c is going to be 2. So then we have equations to solve, because it won't be a, right? It will be like multiple of a and b and c together. In this case, I can see that it's going to be a plus b plus c is equal to 0. So now we have one equation. Then I can see that it's going to lead somehow into something of 3-way equation. Should I do it? Nah, I'm too lazy. Let's leave it like this, but this is the idea of how to do it. We'll do and this is for this one. It's going to go to the 3x3 linear algebra.
It's still in this topic, right?
In this topic. Actually, we'll come back to this when we're doing the 3x3 linear algebra. But let's leave it as this. I think partial fraction on its own is not going to appear on its own, but it's going to appear together conjoined with other topics. Like any other questions here, but especially partial fractions. It's quite supplementary.
What can it be combined with?
What can it be combined with?
Yeah.
Like, for example, the calculus, or it can also be combined with the linear algebra. Like, this question will be a linear algebra problem, right?
Yeah.
Anyways, let's move on. 7, the complex number. So first off, when we talk about the complex number, we need to understand that there are 3 ways to represent the complex number, right? So what are those 3 types? The first type is standard a plus iv style. And the second one is the cosine theta plus I sine theta, or equivalent of saying that cis of theta.
Are there names for the different types?
Yeah, they're in the form of booklet.
Modulus, argument.
Yeah, and exponential form. The first one doesn't have a name, but this one is modulus.
That's like the form A plus IB.
The first one is called Cartesian form.
Oh, sure. Cartesian. And then lastly, it's r e to the power of I theta.
What was the first useful? Oh, the more R.
It's also the shortest, right? It's also the shortest.
Oh yeah.
Right, so actually, the modulus argument has the r as well. I forget, my bad. Let's put the r. My bad about that. So, one thing to note is that Cartesian form is the most useful when you're trying to do addition and subtraction. Whereas the modulus argument form, the exponential form, they're pretty similar. In my opinion, the modulus argument form is just a step between Cartesian and exponential, because exponential is just easier to use anyways, is for the multiplication.
How do you get the exponential from the modulus argument again?
Look at the formula booklet. It literally tells you.
Yeah.
Yeah.
Also, you just know that it's r and theta. It's the same r and theta appears, and the cis and the e to the power of I is the same thing. So, for example, if it's 2 cis pi over 2, then it's going to be 2 e to the power of I times pi over 2.
We just don't need to know the proof of that, do we?
No.
Oh.
It's
You
useful
don't
for
really
multiplication
need to know
or
the proof of
exponents.
anything.
Okay. When you want to solve like the unity of something question. Okay, and how do you go? And we need to know how to go from one step to the other, right? So usually you'll be given the Cartesian form, and if you want to multiply these like Cartesian forms together, then it's better if you switch them to exponential, ultimately through the modulus argument form. Right? So we need to think about the Cartesian form as the on the Cartesian plane, right? That's why it's called Cartesian form. So remember that on the x-axis, the horizontal axis, we have the real value, and then we have the imaginary value. So the real value is the value of a, imaginary value is the b. So then, for example, if I draw out the situation like this, let's say, so this, I can represent it as 2 plus 2i. It means that the real value is 2 and the imaginary value is also 2. So after I draw it out, I can measure the angle and also I can measure the r value. Right? The angle is the, I forget, what's the modulus? What's the argument? It's not important, I think. I think the r is modulus. Is it? Yeah, r is modulus. So we're going to find the modulus r by finding the distance. And how do you do that? Using the Pythagorean theorem. You're showing that this is 2 and this is 2, so the r is equal to
2 times.
the square root of 2 root 2. And then we're going to find the theta by using the trigonometry. So obviously it's a right triangle, so the theta is going to be pi over 4. So then we can represent this as 2 root 2 cis of pi over 4, which is ultimately going to exponentials 2 square root 2 e to the power of I pi over 4. And when you're going the other way, you can do a similar thing. You draw out on a Cartesian plane, you draw out the angle, you draw out the modulus, the radius or such, and then we try to find the x and y coordinates using the trigonometry, trig ratios, easy ones.
Can you repeat what you just said?
Yeah, so if you want to go from exponential form to the Cartesian form, first you draw the exponential form, imaginary number, a complex number on the Cartesian plane by using the r value and the theta value. After that, I can find the real value and the imaginary value, like how you find the x and y values using the sine and cosine ratio, which is pretty simple. If you remember that you have to do that. Process is quite easy. Okay, so that's about the complex number. Cheat sheet. All right,
Can you post this on Google Classroom?
It is already there.
it's already there.
Nice.
Did you not end up taking notes?
Boy, I'm taking notes about what I should be taking notes in the future.
One more thing about the complex numbers. We'll talk more about this when we talk about polynomial equations tomorrow. But the complex roots, right? Complex roots are always appear in pairs, in conjugate pairs. For example, let's say we have a weird equation of x power 4 plus dot 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 plus 1 equals 0, let's say, has a root of, let's say, 3 plus I, let's say.
3 minus I.
Then it means that we also have 3 minus I as a root. Okay? because they always appear in the conjugate pairs. Yes, and then when you multiply them, it becomes real. When you add them, it also becomes real.
Is that 3 plus I and 3 minus I hypothetical for now, or
We're just
Yeah, I got 3 plus I hypothetically, and then I'm just saying that it's 3 minus I. The conjugate pair is A plus BI and A minus BI.
It's 8 plus minus b.
Yes. That's why when you use the poly root finder on your calculator, you'll see the roots, the complex roots, and they're going to appear as the same A value. You basically have two same values, but only after you scroll right, you see the B value. It's the same B value, but it's just plus minus different. You'll see that as well.
What about the other two roots?
Other two roots.
It could be real, or
It could be two real, or it could be two fake. Two fake. Two complex roots.
Like to find them?
To find them? What do you mean to find them?
Like how?
How would you find them? Well, so you can use, if you have a root of 3 plus I, it means that x minus 3 plus I is a factor, right? If an equation has a root of 2, then x minus 2 is a factor.
yeah.
Oh, yeah.
Yeah, so that's why if 3 plus I is a root, x minus 3 plus I is a factor. And also we know that x minus 3 minus I is also a factor, right? Or a factor. Or factors. Then we'll multiply these together. It'll be a difference of square, I'm pretty sure. Or it doesn't matter. Multiply these together, and then you divide the original expression with that, the polynomial division thing. Then we'll simplify the polynomial expression. Then we can attempt to factor that from there more easily. Then we can find the elements. We'll do more of this in tomorrow's review of polynomial equation.
How do you find the complex roots from like polynomial equation?
Use the negative b plus minus b squared minus 4c. Like, you know that one, the
Oh,
quadratic
yeah.
formula. Yeah. If you have that, then you can just if your discriminant is negative, then you can just take I out, and then you have
Right.
Yeah.
Okay.
That's possible when you have a quadratic
Yeah.
equation. If you have more higher degree equations, you can try to simplify. You try to find like one root at a time by using the sum and product rules,
yeah.
and then you take it down in pieces. So for example,
You
somehow you realize that, let's say 1 is a root. Then you go, okay, x minus 1, you divide. So then it goes down to cubic, which is a bit easier. And then you try to find the other one, and then so on. Or sometimes the question gives you hints of where to tackle the problem first.
I don't think, at least paper 1, I don't think they'll tell you to just solve a big polynomial, right? They'll just give you, like the one we did
They'll give you some
yesterday,
hints, yeah.
where it was like z4 plus z3 or
Yeah.
something, and then you did that. They said the fact roots are a plus bi
Yeah.
and b minus something, and
And then
then
you find the real.
Yeah.
okay.
Or you can use your calculator.
Yeah.
Yeah.
just cheat.
If it's on P1, then.
What she said, sit next to Eric. Copy that.
All right, let's move on. One more thing when we talk about the complex numbers is about the De Moivre theorem. So we see that in the formal booklet, the Moivre theorem. Like it doesn't really look like one. Basically, when do we use them? Is when you try to power. When you try to power a complex number to the power of n. So then we can use this to kind of go the reverse way. For example, let's say the z of n is equal to, let's say 1. And then you try to solve, like, what is that? And that's when we use the De Moivre theorem. Okay? I just want to point that out because you see the theorem, and then you're like, what is this used for? And the main part, I'm going to just explain it on the formal booklet here, is that on the first line, on the left hand side, you just see that it's just z to the power of n, right? But then as you go through on the right hand side, you can see that r to the power of n is still there, but now the angle is multiplied by the exponent. So that's the main difference. So that's a way to understand the de Moivre theorem, right? The r value is power to n, whereas the angle, the argument, is multiplied by n. Okay.
What kind of questions can they ask for this?
Like I said, like when you're going to give an equation
Yeah.
like this, and then you can solve that equation by using the de Moivre theorem.
Yes.
You'll have more hints than this for sure. But
Okay.
once again, we'll definitely see some questions, IB exam questions, that include some off there for sure. Right, let's move on to the last part, the linear algebra. Okay, so once again, the linear algebra is tied with other topics, especially the topic 3, when we do the plane interactions. But we have two types of linear algebra, the 2x2 and also the 3x3. Our goal, if you are trying to do this without the calculator, if you have the calculator, you use the Poly Simulator 2. Poly Simulator? Poly Root Finder and Simultaneous Equation Solver version 2. Right? So we do the simultaneous equation solver, the 3x3 or 2x2 and such. That's easy when they're doing that. If you're trying to solve it by hand, it's quite tricky. Well, our goal is to find the row echelon form. So basically, the 3x3 matrix usually looks like this. You have like 1, 2, 3, -1, 0, 2, let's say 2, -1, 0, and then we have the constant term on the other side, like 1, 0, 1. Let's say
This is row echelon.
row echelon form.
Is that?
No, this is
It's
not.
called Matrix.
Yeah. So this is the 3x3 matrix, so 3x4 matrix. Our goal is to go to row echelon form, or reduced, better. But I've noticed that people don't like doing the reduced one.
It's useless.
Is to go for 1 something something, and 0 1 something, and 0 0 1 something. It's called this x y z. Okay. Actually, I think this is the row echelon form. Right? The reduced one is when you have 0 0 0 all the way at the bottom. My bad. I apologize. This is a row echelon form. Going to the row echelon form requires the eliminations and the row operations. For example, you multiply the second row by 2, and then you add it to the third row so that the zeros are formed. Basically, the idea is that you try to fix the 1 on the top left corner, and then you get rid of the first term on the second row. And then you do the same thing, divide it by the coefficient to fix it to be 1. And then you get rid of the other ones as well, and then you fix them. Okay. So this one first, 2, 3, 4, 5. After that, you can just take this out. So now this has an equation of x. It's not, sorry, my bad. Let's not use x, y, z. Let's use a, b, c. It's going to be x plus something y plus something z is equal to a. Y plus something z is equal to b, and z is equal to c. Right. Then we can use the fact that z is equal to c to go back to the second equation. Now we only have one variable, so we can solve that. And then now you know y and z. You go back to the first equation to find x. So that's the basic idea of row echelon form. Should you try the one from the previous one?
Yes, please.
So I just made up this question, so this may work or may not work.
Is that it? Is that all linear algebra is?
Did you fix it?
Yeah.
I just don't know how to do it.
And then there was also like a
What
special
kind of
case where you
button
have
do you
all
use?
zeros and then it's like
Oh, that's for planes and stuff. Where it's like
Yeah, when you try to interpret
that's
them.
for B. That would be topic 3.
Okay, so let's try this. 2 is equal to a x squared minus plus x minus 2 plus b x squared plus 3x plus 2 plus c x squared minus 1. Squared.
yeah, highest level of math I'll ever learn in my entire life.
That's like when you cut someone open and there's a road patch on the floor. You're sitting there like, you're like, oh my god, listening to laugh. No.
3 plus 4i equals pretty much.
Math is fun. So we should.
Okay, so while I'm expanding the right hand side, I've already collected like terms. So we conclude that a plus b plus c is equal to 0, right? And the a plus 3b is equal to 0. And negative 2a plus 2b minus c is equal to 2. Right? So let's take this simultaneous equation into a matrix. So we basically just fill out the coefficients. 1, 1, 1, 1, 3, 0, negative 2, 2, negative 1, 0, 0, 2, put a bar around, and that's my matrix. That's my 3 by 4, 3 by 3, we'll call this.
Negative 2y.
R2 minus R1.
2 skips.
Yeah, so once again, my goal, it's already, the first top left part is already 1, right? So that's fine. So my goal is to attack this one. We're going to attack that one.
Why don't we just flip everything over to write CBA so that the 0 is already at the beginning, so we don't have to do that? Or like do it mirror.
I don't think it matters too much.
It's one step less. That's
One step less. But then by flipping that, you're doing another step. So.
2y.
Anyways, so let's do the operation.
0
So I'm going to leave the row 1 as it is, but I'm going to say that row 2
minus row 1.
row 2 minus row 1 is going to replace the row 2. So that means that it's going to be 1, 1, 1, 0. And then row 2 minus row 1 is going to be 0, and then 2, and negative 1, and 0.
Yay. Now we attack.
While I'm doing that, let's also get rid of this one too. Why not? Right.
R3
So it's going to be row
2r.
2, row 3, plus 2r1. It's going to be r3. Because I want that to be 0, right?
0,
Do we need to write those like
Yeah.
rows?
Yeah, it's pretty.
Yeah, it's helpful for you.
Yeah.
It'll help you.
Yeah, no, no.
Oh, and also when you when one of those values are like a and b where you don't know it, if you don't write that, it's gonna be pretty hard for you to
Track.
yeah.
Okay.
Yeah.
That makes sense. I trust Kenta.
Not bad.
Not bad to trust Kenta.
And then
So at this point, we're already pretty close. At this point, if you want to get off the train and try to solve the latter two equations, systems of equations, that's also fine.
it's easier.
But I'm just going to proceed. So I'm going to divide the row 2 by 1 over 2.
Why don't you do like
It's going to be 1, 1, 1, 0, 0, 1, negative 1 over 2, 0. And while I'm doing that, let's also do R3 minus R2, 2R2. It's going to replace R3. 0, because I want to target this one, right?
0?
It's going to be 0 here. 1 minus 2 times negative 1 is 1 minus negative 2.
3.
There's 1 plus 2, so it's 3. 2 minus 0 is 2.
Okay. You should. That's
Pretty close. And
3z.
and then let's just move on. And you know, let's just do it here. It's going to be 1 here, so it's going to be 2 over 3, right? Divided by 3 on both sides. So yay. So I know that z is equal to 2 over 3.
C now in this case, right?
It's c, yes. My bad. And then we know that b plus c minus 1 over 2, c was 0. But we know that b minus 1 over 2 times 2 over 3 is equal to 0. So b is equal to 1 over 3. Yay. We also knew that a plus b plus c was 0. So a plus 1 over 3 plus 2 over 3 is 0. So a is negative 1.
That's pretty good.
Yeah, why not?
Let's go.
So then we can say that that expression 2 over, what was it? X plus 1, x minus 1, x plus 2. Is equal to a negative 1 over x plus 1 plus b 1 over 3 times x plus 1 plus 2 over 3 x plus 2. Yay.
Yay.
Okay, so we'll finish there. Any questions about the linear algebra? Well, yeah, sometimes we'll like, if it's like 0, 0, 0, and then some weird number, then we say there's no real solution. If it's 0, 0, actually, let's write this down. 0, 0, 0, and n, no solution. Right? Because we're saying that it's 0 equals to n. But 0, 0, 0, and 0 is infinitely many solutions. Are there any other cases?
No.
Sometimes you see the case where R2 and R3 are like basically the same thing. I think we've seen that today actually, where you have like R2 and R3 are the same thing. Then you have like lack of information as well. So there are infinite solutions as well. But yeah, I think that's good. Right, we'll finish there. Thanks for coming, people. I'll stop right there.